Okay guys, this is 15A. Let's get right through. Alright, let's see. Alright, so we're going to look at major air pollutants and their sources. We're going to be able to identify and describe major air pollutants and describe the sources of air pollutants. That's both anthropogenic, or human source, and natural source, right? Alright, air pollution, okay, the introduction of chemicals, particulate matter, or microorganisms into the atmosphere at concentrations high enough to harm plants, animals, and materials such as buildings, or to alter their ecosystems. Air pollution system has many inputs and outputs, so it's worth noting here that air pollution system is a global system, okay, it's a global system. Okay, that means it's kind of like water in the sense that it moves, right? Since it moves, what we do with the air around us affects countries that are proximal and even around the globe, right? So there are traces of mercury in the air from China because China is such a big producer of pollution from coal burning, right? Okay, so that's something to consider. Okay, classifying pollutants. Okay, let's start off with sulfur dioxide. Okay, we're going to go into the criteria pollutants that the Clean Air Act has delineated as things that we need to watch out for. There's 6 of them, and there are a couple of them that you'll be surprised are not on there. Right? But first off, we're going to talk about sulfur dioxide. Okay, corrosive gas that comes primarily from combustion of fuels such as coal and oil. There'll be a chart later that you can see that most of it's going to come from combustion of fossil fuels, and the leading emitter of those or combustion of those fossil fuels are going to be cars, right? Okay, it is a respiratory irritant. Basically, everything that's in the air is a respiratory irritant. Okay, it'll adversely affect plant tissue. Also released in large quantities during volcanic eruptions. So right here, this is a natural source, right? So we got anthropometric up here, anthropocentric rather, and we have natural sources. Okay, forest fires as well. So, okay, nitrogen oxide. The sulfur dioxide, or sulfur oxides, we're going to call those SOx. So easy way to remember that, you might have known this from when Mr. Payne was here. SOx, and we have NOx now, right? This is an easy way to remember some of these, right? And then the carbon monox, right? Carbon monox as well is going to be another one. All right. Motor vehicles, stationary fossil fuel combustion are the primary anthropogenic sources of nitrogen oxides. Again, it is a respiratory irritant, so if you're making a table on the sources and the effects, make sure you always have irritants there and fossil fuel combustion. Okay, it's an ozone precursor, and we're going to get into what that is, and it leads to photochemical smog. Okay, so having nitrogen oxides in the air will produce more tropospheric ozone than would naturally be there, right? We naturally already have a lot of ozone, or O3 in the stratosphere, right? And that helps us from UV, right? This protects us from UV radiation by absorbing and re-emitting it as heat. That's why the stratosphere is so hot, because it absorbs this ozone. It absorbs this UV radiation and re-emits it all over the place, scatters it in the way of thermal radiation. That's why it gets really, really hot up there. So you remember that the hot air rises until it cools, right? But then once you hit this stratosphere, it gets really hot again, right? All right. So what do NOxes do? They convert to nitric acid in the atmosphere, and that's nitric oxide. You need to know that equation. Nitric acid, so that's HNO3, right? Because it's -1, and this is a plus. This is -1 for nitrate, and +1 for this, so it ends up balancing out, right? All right, so this is nitric acid in the atmosphere, which is harmful to aquatic life and some vegetation. In fact, all of our acid rain, when we get to acid deposition, is going to be very, very harmful to aquatic life. All right, this stuff naturally happens, though, even without us. It falls on us, and we aren't usually affected by it just because our skin is a really good barrier to these things, right? But things that live in the water where the acid is deposited, they don't have that same luxury, right? So they're much more affected because they're in that environment the entire time. Okay, classifying pollutants. Carbon oxides, carbon monoxide is the common emission in vehicle exhaust and motor and other combustion processes, especially when you have incomplete combustion. So when you have incomplete combustion, or the oxygen is not all used up, you end up with a lot of carbon monoxide. That's why there are some vehicle safety standards, like not having visible emissions coming out of your car. That's something that was outlawed a while back, and just checking to make sure that your engine is firing properly. If you ever look at that pilot light underneath your hot water heater in your house, if you have a gas one, if you look under there, you should see a nice blue flame. That is a sign of a complete combustion. If you have any other color than that, you run the risk of having incomplete combustion and having carbon monoxide coming out, so be very, very careful with that. All right. In urban areas, we have carbon monoxide. Carbon dioxide is released by burning fossil fuels. Is becoming a major pollutant, but it's funny that it's not actually part of the 6 criteria air pollutants, right? So this is something that we've tried to put on recently, but has been stricken down. This was something that was trying to be monitored more under the Obama administration. All right. Classifying pollutants. So we have particulate matter, or PM, and there are 2 types of PM. You have PM10 and PM2.5, and we're going to talk about those in a minute. So these are particulates or particles. These do have an effect, just like in water. They can clog up our gills if we were fish, right? And they can change the amount of sunlight that gets down to the bottom, right? But this has effects on our respiratory systems, right? And it has effects on the amount of sunlight that can get down to the plants on the surface of the earth, right? If we don't have a lot of sunlight coming in because it's getting reflected and scattered off all over the place, we're going to end up having decreases in temperature over time as well, right? So we can end up with kind of like a weird dusty winter, right? And where do they come from? Naturally, we have volcanoes, wood fires, and anthropogenically, we get them from burning fossil fuels, from burning biofuels like wood, manure, things like that. Road dust, we kick it up like this. If we crush rocks from doing construction, it'll also release a lot of particulate matter. And it's worth noting, like, when we have large meteor impact strikes or asteroid impact strikes, a lot of the damage, of course, you let off a big shock wave from the kinetic energy of the projectile hitting the Earth, but you also have most of the damage is from afterwards, from all this particulate matter that covers the surface of the Earth, right? And it's in the atmosphere for hundreds of thousands of years sometimes. So that's really what the major problem is with impact strikes. All right, so haze, it just means reduced visibility. Photochemical oxidant is a class of air pollutants formed as a result of sunlight acting on compounds such as nitrogen oxides. Make sure you connect these things together. Nitrogen oxides with sunlight, right? And especially ultraviolet, right? The ultraviolet's going to have a lot of energy and be absorbed by nitrogen oxide. Okay. All right. O3 is a secondary pollutant made up of 3 oxygen atoms bound together. And it's worth noting that the first 2, so O2, has a nice double bond, which is pretty stable. But the third oxygen that makes up O3 is a single bond that's not very strong. Okay, and so that UV radiation will come in and break this guy up, right? And that's really what's happening here. So you'll break this up, you'll break up the ozone. So in the upper part of the atmosphere, if you do things like CFCs, so in the presence of CFCs, are chlorofluorocarbons, right? When these guys get up in the atmosphere, they jack things up, right? Because they'll get in, and the chlorine from the chlorofluorocarbons will break up from UV radiation and then interact with this guy and combine with the released oxygen atoms. Okay, so that's bad. All right, smog, a type of air pollution that is a mixture of oxidants and particulate matter. Okay, and this has effects on human health. All right, photochemical smog, dominated by oxidants such as ozone, and this is known as the Los Angeles type of brown smog, right? Sulfurous smog, on the other hand, is sulfur dioxide and sulfate, and this is gray or London smog. All right, lead is one of our criteria pollutants that definitely has a big health impact on human health. There is no safe level of lead in either our water or atmosphere, so it's heavily regulated. It used to be a gasoline additive, mostly in the United States, found in coal, oil, and old paint. Right? Kids, the joke used to be, did you eat paint chips as a child? And what that was is old school paint used lead, and when it would chip off the wall, it has kind of a sweet flavor, and kids would eat it, right? The Romans used to sweeten their wine with lead, right, if it was sour, kind of going old. Yeah, this impairs the central nervous system because it mimics zinc ions, okay? And zinc is used for neurotransmitters and things like that. So since it's very similar molecularly at that level, it'll get absorbed by different neurotransmitters, axon terminals, and things like that. But it won't be broken down the same way that zinc is, so it'll stay there and kind of jam up things and eventually necrotize nervous tissue. Okay. At low concentrations, can have measurable effects on learning ability and our ability to concentrate. In fact, kind of an interesting aside here, violence, levels of violence and crime and murders have gone down with the decrease in lead in the air, water, and manufacturing. So it's very, very interesting, right? Okay, VOCs are organic compounds that evaporate at typical atmospheric temperatures. There are natural VOCs, but the ones that we really, really care about mostly are going to be the ones that are anthropogenic in nature, such as fuel, solvents, paints. If it has that clean laminate smell or that clean kind of finish smell, it's a VOC, right? So you might have gone to the store with your parents or maybe by yourself to get like a can of paint, and you notice that some of the paints, when you open them, they don't really have that really strong paint smell. That's because they are low VOC. They're low VOC. All right, and these have an effect on our health because they are precursor to ozone formation. And I know what you're thinking. Well, we just talked about ozone in the stratosphere, and that's good for protecting us against UV radiation. But a lot of the times, this stuff will get stuck in the troposphere. Did I spell that right? I did not. There you go. There's a P right there. Troposphere. And tropospheric ozone is not good for us, and we're going to learn about that in just a second. Why? All right, so let's first get into the idea of primary and secondary pollutants. So primary pollutants are things that come directly out of some sort of stack, exhaust pipe, or natural emission source, right, like a volcano or something. Okay, and these examples usually include things like carbon monoxide, carbon dioxide. Remember that carbon dioxide is not one of the criteria pollutants. Right. Sulfur dioxides or SOx, and then NOx, right? And they're suspended, they're most suspended particulate matter. All right, secondary pollutants are things that happen after a transformation due to exposure to sunlight, UV radiation, right, or just heat, water, oxygen, or other compounds, right? So in the presence of these things, you can form chemicals or pollutants that are harmful. Okay, examples of that are ozone, sulfate, and nitrate, right? These are nutrients that we're learning about in our water cycle, and we're applying to our ecocolumn right now. So how do these things lead to pollution? All right, let's look at this graph here. Okay. So you see our primary pollutants here come from things like volcanoes, smokestacks, driving, from homes, right? Burning things, burning fossil fuels. And what's going to happen up here is they end up condensing into clouds. And what's going to happen to them next, right? So these things lead to our secondary pollutants. Right? So we end up with, I want you to see kind of like this transformation here. So look what happens to our sulfur dioxide, combines with oxygen, right? With heat and things like that. Look at our sulfates. So sulfur dioxide, sulfates combine with water molecules up here with heat, and UV radiation becomes sulfuric acid. All right, we got nitric acid here. And we have peroxides, things like that. All right, so you see here, the transformation from primary to secondary requires a number of factors, including sunlight, water, and the appropriate temperature, right? So at nighttime, a lot of our secondary pollutants will kind of decrease, right, because we lose the sun. Okay, air pollution comes from both natural and human sources. Natural emissions include volcanoes, lightning, forest fires, and plants. So the lightning's kind of cool because the lightning will turn molecular nitrogen, or diatomic nitrogen, N2. Sorry, it's kind of nasty. This will turn into this guy, right, through a process, right? Okay, anthropogenic sources include on-road vehicles. So again, the vehicles, hit the vehicles hard, right? And how do we decrease anthropogenic sources of air pollution? Well, you got to stop driving. We have to drive less. We have to figure out ways to carpool, use public transportation, use alternative fuel sources. The anthropogenic emissions from human activity are monitored, regulated, and in many cases controlled. Some anthropogenic sources are on-road vehicles, power plants, industrial processes, and incineration. The Clean Air Act and its various amendments require the EPA to establish standards to control pollutants that are harmful to human health, and welfare, right? And there's a very specific definition of human health in your book that I'd recommend looking at. And welfare has to do with ways that humans use air to make money or sustain or be able to live, like agriculture. And human health is talking about like our respiratory problems. And through the Clean Air Act, the EPA was able to establish this National Ambient Air Quality Standards, and it specifies the concentration limits for each of our 6 criteria air pollutants. So let's look at that. All right, so here's just a graph to drive home the emission sources. And look here, transportation is the largest. So look here, on-road vehicles, non-road equipment. You see everything else really pales in comparison. So if we really want to hit stuff first, look here, like electricity generation. Even when we do things like burning coal, look at how much less of an impact it has on air pollution compared to on-road vehicles, right? So if you had to make the decision between driving a fossil fuel car with less combustion of fossil fuel, like very, very efficient, or just using an electric vehicle and charging it and having that charging come from an electrical generation using coal, this is still much lower than look at what we're doing now, right? If we can change all of these, or at least a good percentage of this, into electric vehicles and just charge off of electricity through like a grid, we would greatly decrease the amount of air pollution, right? Okay, let's look here. So that was for carbon monoxide. Look at nitrogen oxides. So our NOx is here. Even NOx, right? It's still the same thing. On-road vehicles are the majority. Electricity generation's up there, but it's definitely, a little bit over half of what this does, right? So if we could decrease this and maybe rely a little bit more on this, and who knows, maybe invest in things that are not going to burn fossil fuels, right? Wind, hydroelectricity, solar panels, right? All right, continued, let's look. Okay, sulfur dioxide, SOx. So electricity generation is the majority of this one because we're using coal, right? And we know that coal has a really big percentage of that, right? Okay, so this is the one that isn't really caused by on-road vehicles, right? Because we're not using coal in our vehicles. So keep that in mind, right? So on-road vehicles kind of flip with electricity generation here. Okay, let's look at particulate matter, PM 2.5. This is the one that's really, really harmful because PM 2.5 is really harmful because it gets way beyond the filtered hair that we have in our nose and throat and lodges itself really deep in our respiratory system. And in addition to that, it's really small, so it's usually accompanied by other very harmful chemicals. Okay, so where do particulate matter come from? Okay, road dust, miscellaneous, great, awesome. That's very specific, right? Industrial processes, but it's worth noting that it's road dust, right? So what do we get road dust from? Driving. So again, it's linked to some sort of either not having trees to anchor soil down or just moving around, right? We still get some from electricity generation, right? Stuff that comes out of smokestacks and things. There are ways to stop this from being much higher, right? If we look at electrostatic precipitators and things like that. All right, so you really want to know this chart here. Look at which one came down the most. Lead, because we outlawed the use of lead in our fuels. This is going down quite a bit, right? Ozone, not so much. In fact, ozone is over the standard, the percent-wise. These don't all have the exact same standard. That's worth noting, right? This is just a percent deviation from the standard, right? But ozone is still, it's going down, but look, it's kind of on an uptick, right? Okay, particulate matter 2.5, particulate matter 10. Anything above 10 micrometers in size, our nose and throat filters out really well. Okay, carbon monoxide going down, everything's going down because of the Clean Air Act. Right? It's that national ambient air quality standards have really been good to kind of establish a criteria for us to try to keep these things and decrease them. All right, let's look at photochemical smog and acid rain. Okay, we're going to look at the equation for photochemical smog and why it's still a problem in the United States. Describe how acid deposition forms and why it's improved in the U.S. and become worse elsewhere, right? AKA who's still using fossil fuels a lot, right? All right, so here, let's look at ways we can decrease smog. Maybe if we just quit smoking, right? There's too much smog in the air, right? So this is what will happen to us. Right? We'll all look like this if we grow beards and become these very small Irish people. I thought they were Irish people. I mean, who were we kidding? They're Scottish Irish people. Oh well. All right. The formation of photochemical smog is complex and still not all the way understood, but we're going to look at some of the things that go into it. All right, so this picture here is very, very important. Okay, so normally, right, this is how ozone forms, right? This is how ozone forms. So you start out with nitrogen dioxide, and in the presence of sunlight, UV radiation, it'll break this up into, you notice conservation of mass, 1 nitrogen atom, 2 oxygen, 1 and 2, right? Breaks this up. This oxygen atom will form with diatomic oxygen to form O3, and I told you that there's a double bond, a single bond, and at nighttime this will break up, right? Okay, so natural ozone accumulation works like that, right? And this is good in the stratosphere, like we said before. Okay, now natural ozone destruction. So in the presence of, or the lack of heat and the lack of UV radiation, this will break back up into the components. So it's basically just the reverse process, right? It'll go this way in the day, this way at night. Notice the sun's going away, right? Okay. Now, here's what happens to some of that nitrogen oxide, right? The nitrogen monoxide, if there are VOCs, volatile organic compounds. So some of them will do the natural process of ozone, which will create a little bit of heat and refract some of the light, deflect it, and scatter it all over the place. But if you have VOCs, you have these photochemical oxidants, which will scatter that light so much, and it'll keep the heat there even when the sun is gone. So you're not going to have this natural breakdown here back into nitrogen dioxide and O2. So what you're going to have a steady buildup of ozone, which can't be cycled back into the sky very quickly, right? And so you end up with an overaccumulation of ozone, right? And in the troposphere, that's a bad thing. It's a really bad thing because you end up with temperature inversion. We'll talk about that in a second. All right, thermal inversion. Situation in which relatively warm layer of air mid-altitude covers a layer of cold, dense air below. And how does that happen? From an increased layer of smog. Yeah. The warm inversion layer traps emissions that accumulate beneath it. So usually you have things that you have like a really big hot layer of air right here. Well, what's this stuff going to do as it goes upward, right? As it goes upward. Well, it's going to cool down, right? Let's see if I can get another color. All right, so there we go, orange. Yay. Okay, so you see this like orange stuff, it's spreading out more. And we end up with like yellow here, kind of. This stuff eventually cools down as it goes up, right? And it spreads all over the place, and it has more volume to go into, so that's a nice thing, right? That's really, really nice. Okay, but when you have this O3 that's going to like block it in, and you have smog that's going to block it in, what ends up happening is you end up forming this nice red layer right here, and now this stuff can't rise. The cool air can't come back down. Okay, the cool air is not going to be able to come down. It's going to get trapped right here. Okay, so what ends up happening is you end up with all this crap, all this like gunk in the air, these green circles of gunk, and it stays there, right? And it affects the health of the people below it. Okay, so let's look at a picture of that. Okay, so during the day, warm, cool air, and then it rises up, right? The warm air rises, becomes cool. But look what happens here. You see that as the altitude goes up, the temperature decreases, right? Look what happens if you have this smog that builds up. You end up with this cool stuff trapped right here instead, and you end up with problems. All right, let's talk about acid deposition and wrap this thing up. Okay, it occurs when nitrogen oxides and sulfur oxides, in other words, the precursors to nitric acid and the sulfuric acid, they combine with atmospheric oxygen and water, which has the hydrogen atom, right? And that's going to give us our sulfuric acid and nitric acid. The secondary pollutants further break down into nitrate and sulfate. So when they hit the water, right, or when they hit the water in the clouds, they're going to dissociate, become nitrate and sulfate, and we're studying these nutrients right now, right? And that's going to increase those nutrient levels, and also it's going to lower the pH. We have a reduction of acid deposition because we're not having as much sulfur dioxide. We're not burning off as much of the coal stuff as we were before. And if we are, we're using things like wet scrubbers, dry scrubbers, and hydrostatic precipitators. Okay, so let's look at the picture of how this works. So we got primary pollutants here. NOxes and sulfur dioxides go up in the air. In the presence of O2, secondary pollutants, sulfuric acid, nitric acid, will break down into hydrogen ions and sulfate, hydrogen ion and nitrate, and then it comes down into the rain. It's really going to affect aquatic life, because guess what? All this stuff is going to do what when it hits the ground? It's going to run off, right? It's going to run off and go into the water, and things that have a very narrow range of survivability and fitness in the water are going to be affected when you lower the pH. Okay, well, here's that slide now. Okay, lowering the pH of lake water, and if things can't live in there, guess what? They're going to die. And those species that can't tolerate those ranges are going to diminish, and you have a decrease in biodiversity. Remember I said basically every chapter you should be able to link in biodiversity, habitat destruction into everything, right? So make sure you do that. Also, it's going to, since we're talking about chemistry and ions, you have to remember back to like soil, like your cation exchange capacity and things like that. Because you have hydrogen ions that are free, they're going to sometimes be more favorable reactions. They're more active than the metals like aluminum ions and mercury ions, right? And there's a couple of ways that can be an ion, but what it'll end up doing is it'll mobilize those things out of the soil and out of the minerals that would, that they're locked into inertly, right? They're not doing much with anything around them, but because you're introducing a lot more of these other cations, they're going to switch because they're a higher activity level, right? So they'll switch, or they're a lower activity level and switch. So they'll switch out, and then you'll release these into the water, and obviously, having things like mercury in the water are not good for aquatic life. Having aluminum ions in the water are not good for aquatic life. On the human level, what do they do? Biologically, not much, because we have good skin barrier to block these things out and buffer us from extreme changes in pH. Unless we get it by just 12 molar hydrosulfuric acid or something like that. Okay, but it will affect the calcium ions. It will affect the calcium ions that are in our monuments and buildings. So you can see examples of melted faces of statues, right? Which sounds really gnarly and everything, but that's the effect that it has on human development, right? All right. Well, I hope this was helpful, and good luck.